The man who sees consistency in things is a wit. The man who sees the inconsistency in things is a humorist. G.K. Chesterton. Good morning. 2048 year problem. Yes, Archimedes' principle and gravity have a 2048 year problem. 2048, quite a peculiar number. One of the numbers within the Fibonacci sequence. Its digital number is equal to 5. Anyways, let's not go into that right now. Typically in these mornings in the daytime, at least this week and the next week, you'll most likely see the American robins being produced, just a live feed. Just because it's just a weekly or bi-weekly event, the American robin eggs haven't hatched yet. So you'll end up seeing that during the daytimes. But I am very behind in a lot of things, and just to show you what material I have to present. I have a list already. These are things I've already looked into, but I'm behind in leaving a breadcrumb trail of things that I wanted to show people. This is this one. These aren't going to be in any particular order. They might go in this order. They might actually skip a few. Who knows? But these are things I've been looking into, things that I want to share, things that aren't easily seen. Some things are easily seen like this, but I want to revisit it and show people. The North Wind is just basically fairy tales and mythologies. The Mayan cardinal colors are the directions. I think I need to add that. The cult commonality of the Jesus story. J.K. Chesterton taking a look at fairy tales, revisiting the lost continents of Mu, Lemuria, and Kumar Kingdom. The interesting thing about the numbers 72 and 73. So those are the things that I am gonna try to make videos of. I am behind schedule, and when I'm not making these videos, I'm researching. So we've got this little balance here where I need to, well, I don't need to, I'm going to, and I do research into these things and these topics, but just to give you ideas where to go to look at these yourself. Again, most of the time I am looking up the mainstream results of these, and those mainstream results are going to be through Google. Most everybody will, because when you're going to go look at these things, you're going to find them there first, because everyone's starting to just go towards the most used thing, unfortunately. But that's the way things are. You're not going to find a lot of these things hidden away on DuckDuckGo and the deep vastness of the web, but who knows. Now, one of the things that I want to showcase in this video is the problem with Aristocrates' principle. And this is a big compilation called Globe Earth Declarations. Basically, it's just to say not Aristocrates, Archimedes, sorry. It's just to showcase, just, you know what, this is what people are going to look into when they look into Globe Earth. I don't want people looking into Flat Earth. Flat Earth has its own problems. Snake pits among them. It's hard to get in on these conversations. Nathan Oakley's Flat Earth debates, but they're interesting indeed. This morning, he started talking about conspiracies, and oh man, I wish the panel was not full. Anyways, Archimedes, 250 BC, any object totally or partially immersed in a fluid is buoyed up by a force equal to the weight of the fluid displaced by the object. In simple terms, the principle states that the buoyant force F to B on an object is equal to the weight of the fluid displaced by the object, or the density P of the fluid multiplied by the submerged volume V times the gravity G, or FB equals P times G times v. Thus, among completely submerged objects with equal masses, objects with greater volume have greater buoyancy. This is a topic that gets discussed quite often within the gravity and density sphere, and buoyancy is part of it. The problem with this is Archimedes in 250 BC didn't know about gravity, so why is gravity in the equation? Gravity, of course, if you know throughout your mainstream media or mainstream official history books, whatever, Isaac Newton is the one who came up with the formula, but of course it wasn't measured until you get to Henry Cavendish, and now I'm talking about gravity, which he measured it 111 years later. Anyways, let's just say that don't trust me. No, just don't trust the information. Vet the information. And if you're going to vet the information, you're going to come up with the same information. So let's look at Archimedes' principle. And let's zoom in to 200%. I think it's a little bit easier to see in 200%, and you can look at different types of things. This is where I got the image for the original. It talks about let's look at this. This is funny. Oh, did I just close it? Shit. Let me let's just start at the beginning, okay? Now, Archimedes' principle, we'll just look at the first 3 results, okay? Because most people are going to look at the first 3 results. There's Archimedes' principle at Britannica.com, Archimedes' principle at Wikipedia, Archimedes' principle with the physics.webr.edu, Archimedes' principle and the Encyclopedia Britannica. Well, I already had that up. Let's just close that. All right, so it goes through a lot of different stuff, but we're just wanting to find, well, more stuff. Oh wait, did I see the? All right, here. That's something else. It goes into what is Archimedes' principle, and again, it's a body at rest in a fluid is acted upon by a force pushing upward called the buoyant force, which is equal to the weight of fluid that the body displaces. If the body is completely submerged, the volume of fluid displaced is equal to the volume of the body. If the body is only partially submerged, the volume of the fluid displaced is equal to the volume of the part of the body that is submerged. There you go. Archimedes' principle is very useful for calculating the volume of an object that does not have a regular shape. The oddly shaped object can be submerged and the volume of the fluid displaced is equal to the volume of the object. It can also be used in calculating the density or specific gravity of an object. For example, for an object denser than water, the object can be weighed in air and then weighed so when submerged in water. When the object is submerged, it weighs less because of the buoyant force pushing upward. The object's specific gravity is then the object's weight in air divided by how much weight the object loses when placed in water. But most importantly, the principle describes the behavior of any body in the fluid, whether it is ship or water or a balloon in air. Now, here's the thing. The density of an object is going to be pretty arbitrary, whatever it is. It's saying, hey, this is the density. How do you measure it? You know, just like anything else. How do you get what is a meter? How do you get the distance of a meter? How do you get the distance of a foot? You know, all of that stuff. That's just whoever came up with it. And interesting thing, I believe the meter came from the distance from the North Pole going to France or something like that. I have to really look that up again. I think that is something that I need to go ahead and note for another feature on topic, and my list keeps getting bigger and bigger because the thing is, I mentioned a lot of these little snippets in between different on topics. The problem with that is, well, you're gonna have to look, it's gonna be hard to look for it, but if I do a specific on topic of it, you can go ahead and look at it within keywords. So if I say, hey, where did the distance of a meter come from, I can go and give you that, and the peculiarity of that from how they came up with that back in that day will be an interesting one, right? So I'm gonna look that up again, and plus I forget a certain amount of things, so looking that up is good. Okay, going back to the subject, specific gravity of an object. So I looked over, so density, however they want to define that by, it's an arbitrary measurement. Now, specific gravity of an object, of course, if you come up with your density, your measurement for that, you've got your volume. Now you can figure out your specific gravity. So if you had the equation for this and back in 250 BC, why did it take 2048 years for the equation for gravity? You could have done it within the 2048 year time frame. Because if you've got the density and you've got the volume, you get the buoyant force, you've got the specific gravity of an object. Because you can get the buoyant force by, again, using this equation, which they don't have, which is the volume of fluid displaced is equal to the volume of the body. Right? And that's how you get the buoyant force, which is equal to the weight of the fluid that the body displaces. So if you get the buoyant force because all you're using is weight and volume, and when you get that weight and volume, now you've got the density or specific gravity. So you've got a problem here with just this aspect. Within 2048 years, gravity could have been calculated, but it took Henry Cavendish and, of course, Newton to come up with gravity. And then the other problem with the 2048 year time differential is, well, why are everyone, sometimes I don't use the right words, do I? Why do the three people who explained the Archimedes principle all have and use gravity in their equations? Because, look, Archimedes' principle didn't include gravity, probably, most likely, right, in his equation for buoyant force. But, watch, we're going to click on these three videos. I'll probably have to mute it so I don't get any additional strikes, but who knows? All right. And of course, this is Khan Academy. You're going to see that G in there for gravity. All right. Can I take that out? No, it's embedded. Stupid. But basically, look, it's H plus D. That's our total depth times gravity right there in the bottom. If you go into the closed captions. And then let's look at Manakoa Academy, okay? Let's keep going, right? Goes into some of that. That's great. Let's see. Gonna make it easier. Open transcript. And we'll talk gravity. All right, 1030. At 1030. So this is another method of just finding things easily. Not all things include transcripts, but of course, if they do, just open up transcripts and you can do a keyword search for a certain term. Where it says here, where G is the acceleration due to gravity. Now, right. So you're gonna see weight equals mass times gravity. Mass equals volume times density. Upward force equals volume times density times gravity. So this is the second video of the top 3 search results within a Google search when you're searching for Archimedes' principle. It's including gravity, and of course gravity wasn't measured until 2048 years after Archimedes.
Hey, it's Professor Dave.
Principle. Let's see if he has a transcript here. Good, he does. Let's do a search for gravity. Gravity is 217, which is mentioned. And here we go. I think we'll move it over. He has to say it, so let's hear him saying it.
Mass of the displaced fluid times acceleration due to gravity.
Acceleration due to gravity. Now, gravity, of course, wasn't discovered until Newton, right? So Isaac Newton discovers gravity back in 1687 AD. Now, Archimedes' principle, again, he didn't come up with it until 250 BC. And do you want to know why? Let's see. Archimedes' principle on floating bodies, Archimedes suggests that circa 250 BC. This is the Wikipedia for Archimedes' principle. Okay, let's keep it at 200%. And then here's also the formula. This is a little bit easier, right? Weight of displaced fluid equals weight of object in vacuum. Oh wait, where did they get the vacuum? Well, weight of object in fluid. And then you've got more additional things and refinements and a whole bunch of other stuff. But, right, everyone is including the gravity part of Archimedes' principle. I would love it if they just didn't include gravity at all, because Archimedes didn't know about gravity. Unless otherwise it would have been attributed. Gravity would have been attributed to Archimedes, because hey, Archimedes came up with it in Archimedes' own principle. But of course that's not true. And you got the top 3 videos here by Khan Academy, Manako Academy, and Professor Dave Explains, all having gravity in the equation for Archimedes' principle. So everyone's gonna think, oh, gravity. Archimedes figured it out way back in 250 BC. Again, the 2048-year problem with Archimedes' principle and gravity. So, if we're talking about Archimedes' principle, best leave gravity out of it. You've got it without gravity here, right? Physics.webrd.edu. Thank you. Archimedes' principle: the buoyant force is equal to the weight of the displaced water. All right, that's easy. That's all it is. Yet everyone starts to add in gravity with it, that you can figure out the gravity or the density of an object based on Archimedes' principle. Well, if that was true, then why didn't in 2048 years did gravity not have been measured by this simple principle? These are the inconsistencies that you find throughout looking into the globe Earth model. And these inconsistencies aren't ever talked about or mentioned within these debates or conversations. And I'd like to go ahead and always add these things going. Oh yeah. By the way, for those who haven't seen yet, I have my mega hat. My mega hat. Let's go ahead and move it on over to here. All right, my mega hat. Make Earth globe again. Any globe earther that wants to swing on by and convince me to become a globe earther again and say, hey, you know, stop being a crazy flat earther. Come on in and what is it? Invoke Mega Man, which is make Earth globe again. Invoke Mega, and we'll do a show. This is called Mega. Make Earth globe again. And so if I have anyone who wants to talk with me or convert me back to the globe side, then, you know, invoke Mega. But you know what? I doubt anyone is going to, because I don't think they're going to want to convert me back. They think it's probably hopeless. But again, if you want to try, I'm here for you, because I don't know what's the point of you making 100 or 1,000 globe Earth videos. It's already been proven by the brightest scientific minds throughout history, correct? Or if you're saying no, then you're crazier than I am. So what's the point of an everyday person making hundreds or thousands of YouTube videos stating that the Earth is a globe? It's obviously a globe if the brightest scientists have already proved it. You're not going to prove anything. You're in that system where your ego or your placement within the pyramidal scheme is important. So if you're on the very bottom of the pyramid, I'm sorry, no one cares. If you're on the top of the pyramid, yeah, maybe they'll push you. But you know what? The thing is, when you're on a flat Earth, it's not a pyramid scheme. It's a flat scheme, so everyone's equal to each other. So that's why I make hundreds or maybe even thousands of videos of maybe even flat Earth. Or if Earth is flat, then let's look into this again. It's revisiting everything, and we're even going to revisit a lot of things as such as fairy tales and mythology, because I think there's a reason why it's told verbally and even written down as kids. And when you grow up and you learn a few things and you're telling it to your kids, you realize that there's a second story beneath that initial story. Because when we first listen to it as kids, we think of something else. When we listen to it as adults, we realize, hey, there's deeper meaning behind this. And then there's going to be even a third time when we look into it that there's something totally different than the first and the second time. So not only do we have to revisit things twice, 3 is a very peculiar number, isn't it? So you're going to look into things 3 times. Hi, C Oddity. How's it going? All right. So this is going to be the end of this on topic video. Just think about it, look into it. 2048 year difference between Archimedes principle and gravity, and we'll see you on the next one. Thank you.